I think we are live, just waiting for it to show up on the YouTube studio. And yeah, hello everyone, my name is Sahil Khose, and today we'll be having a 12th paper presentation. I will be presenting you the paper QANet, which stands for Question Answering Net, and the title reads as Combining Local Convolution with Global Self-Attention for Reading Comprehension. So this paper was accepted as a conference paper in ICLR 2018, and this was one of the first papers which use the self-attention mechanism and convolution neural networks for a natural language processing task, specifically the question answering task that we have. So there is a very famous dataset called SQUAD, which stands for Stanford Question Answering Dataset, and it is a benchmark for question answering problems. So what do I mean by that? So we have a reading comprehension like we have in our English tests, and there are a bunch of questions that the model is expected to give the answers for. Now the answers are not complex in the sense that we have to interpret and understand the comprehension and then generate our answers of our own, but the answers are embedded in the question, in the comprehension itself. So what we have to do is we just have to highlight the part of the comprehension that that answers the question. So this paper, as you can see the timeline of it, it was published in April 2018 or something around in 2018, and Vaswani et al. Came into the first year of 2017, of like first half of the year of 2017, and released the Attention is All You Need paper. From that time onwards, people started using self-attention and convolutional neural networks for natural language processing problems, and this was one of the first papers who got results which were on par with the state of the art, but with a lot of capabilities that self-attention and convolutional neural networks have for natural language processing, which is extremely fast training as compared to before, and also faster inferences, just because the recurrent nature of recurrent neural networks that were used before 2017 were it requires us to it requires the process, like the delay that we have to processing the previous inputs to get that hidden state and then use it for the next time step. So we can't do this parallelly, as we are dependent on the previous hidden states in a recurrent neural network. Hence we can't parallelize the code as we do with like batches when we're using GPUs, and that couldn't be achieved in RNNs because we couldn't infer or like find out the hidden states parallelly together. We had to wait for information to be passed on from the previous hidden state, and hence this gives us a lot of speed improvement, especially in training as well as in inference as well. So the reason that this paper was chosen by me was back in June and July 2020, me and my friend we started to explore the field of NLP through the Stanford's famous course CS224N in natural language processing, and as we completed all the assignments and the lecture course, this was the paper that we chose for our final project that we wanted to implement, and this was the first architecture that we got into, read in depth, and then implemented it to solve the question answering problem. At the time of this paper, SQUAD was the standard for question answering problems, but last year we also had access to SQUAD 2.0, and our efforts were to solve that problem. Moving ahead, this paper has not been pre-annotated as this was the first paper, and the ideas that they display are pretty simple, but they are revolutionary because they were the first ones to use this and reproduce the results. So we'll annotate along the way, and we'll see just how fascinating we get the results with a very simple architecture using convolutional neural networks for natural language processing. So this paper was by authors from Carnegie Mellon University and Google Brain, and we'll move on to the abstract now. as we can see, current end-to-end machine reading and question answering problems are primarily based on recurrent neural networks. We also had attention, but it was in recurrent neural networks itself. So we used to compute dot products with we have a query, a single query, and we have a lot of context that we want to find its relevance on, especially in machine translation. So if you have English to German, then while we are in the decoder part, when we have a German word to be produced, it used to attend on like all the inputs in the English statement and get a weightage for all the words in the encoder input, and then we saw a pattern that it used to get higher weights with the corresponding word that it was translating at that time step. And so attention was there in recurrent models, but self-attention and convolution neural networks weren't used in the natural language processing. So as they said, we did have RNNs with attention. Despite their success, these models are often slow both for training and inference due to the sequential nature of RNNs. We propose a new question answering architecture called QANet, which does not require recurrent networks. Its encoder consists exclusively of convolution and self-attention, where convolution models the local interaction. So CNNs are viewed in a way that models local interactions, as we have a kernel and it attends to the neighboring words and phrases. So convolution models can be seen as local interactions, and self-attention models global interactions. So one thing with CNNs was that the kernel size is small enough and it does not achieve a larger window size than what would a LSTM have achieved. So the improvement that we got with self-attention was with literally no computation, like as LSTM had diminishing gains or diminishing results of attending to previous context. We don't have that was solved with attention, as with just all the connections were directly joined. So the middle of the sentence could have access directly, like there's a direct connection from that particular sentence to the top of the paragraph or the last end of the paragraph and anything that we wanted. So but in LSTM it just dependent on one or like two cells which carried forward all the hidden states and information that it had to store. So with distance it used to diminish, but in attention we directly got access to everything, hence calling self-attention as global interactions. So on the squad data set, we'll see the fascinating results that they get. Our model is 3 times to 13 times faster in training and 4 times to 9 times faster in inference, and these are like manifold speed improvements for training as well as inference, while this is important, while achieving equivalent accuracy to recurrent models. So the one of the best models that existed to solve this problem was BiDAF. We'll see ahead, bidirectional architecture which solved question answering, but this model was able to achieve similar results, comparable results, along with 3 times to 13 times faster training and 4 times to 9 times faster inference, which is really amazing. So the speed up gain always allows us to train the model with much more data. This was another improvement over the recurrent models that we have. Now that we have all these like speed up gain, we could experiment with more amount of data, and that's how BERT came into existence, and now GPT-3 and Jurassic one. I don't remember the name, it just came out yesterday. So yeah, all the big language models, like the Jurassic model that I'm talking about, it came out yesterday, and it has like 5 billion more parameters than what we have in GPT-3, and it shows that it outperforms GPT-3 in a lot of benchmarks. So like not deviating, getting back to our paper, So that's what they mentioned here as well. The speed up gain allows us to train the model with much more data, and we'll see how they generate this data as well. So we hence combine a model with data generated by back translation from neural machine translation model. So we have a context, we have a text in let's say all of this task is done in English. Now we have neural machine translation model which back translates the data that we have. So we have English, then we could have a middle language, which, well, let's say German. So English to German, we translate it. We'll get some translation, different translations, as we don't have fixed translations, which fixed translations. It could vary with the translation and like different ways to interpret the same sentence is also is possible in NLP. So we have like different translation, and then we translate it back to English. We will have a lot of more English data, which means the similar to the starting statement, but it varies in it varies in the words that it is represented by. So on the squad data, we'll see the results now. On the squad data set, the single model trained with this augmented data achieves 84.6 F1 score on the test set, which is significantly better than the published F1 score of 81.8. So the best published best published F1 score was 81.8 by during the time of release of this paper, and they achieved 84.6 F1, which is almost 2. It is a 2.8 increase in F1, which is very remarkable. Now we have a note here. Actually, it says, while the major results presented here are those obtained in October 2017, our latest scores in 2018 April is EMF1 is this for single model, and EMF1 of this for ensemble. So for ensemble they got F1 89.7 instead of like 84.6, which is like a massive improvement. Both ranking number 1. This is important. Even in 2018, these ranked number 1. Notably, the EM of our ensemble is better than the human performance of 82.3. We can see the EM. So EM stands for exact match. F1 scores obviously F1, which is harmonic mean of precision and recall. So the exact match metric for human performance is 82.3, and their single model is just on par. It misses by 0.1%, and their ensemble obviously beats it by more than 1%, 1.5%. So that is amazing. Like being able to perform a task such as question, like as complex as question answering, better than humans, or like on par with humans, is very remarkable. So that is the reason why this paper is so important. Now we'll go we'll go ahead to the next section. Now we see that the most successful model generally employ 2 key ingredients in solving these problems: a recurrent model to process the sequential inputs, and sometimes an attention component to cope up with like long-term interactions, where LSTMs were introduced for long-term interactions instead of RNNs, and because also of exploding and vanishing gradients, but still the capacity for it to store and attend to previous or more importantly previous context diminished when we add longer and longer paragraphs as we require in a question answering setup. So attention was used for that. So successful combination of these 2 ingredients was the bidirectional attention flow model, BiDAF, and we'll be comparing in the entire paper. We'll be comparing how we have outperformed, or this paper has outperformed the BiDAF model. Not necessarily in terms of accuracy or like other metrics, but in terms of speed improvement that it has achieved. And due to that, obviously, after they worked more on it, they stood rank 1 and trained it more and got really excellent results. So probably by that time they did surpass the BiDAF model in terms of metrics as well. The key motivation behind the design of our model is the following. Convolution captures the local structure of the data, while the self-attention learns the global interaction. The additional query context query attention module is a standard module to construct the query aware context. Okay, we'll see this in their experiments. Again, they mention 3 to 13 times faster training and 4 to 9 times faster inference. As a simple comparison, our model can achieve the same accuracy. Okay, we'll change colors. It can same accuracy of 77 F1 score as BiDAF model, right, within 3 hours training. That otherwise should have taken 15 hours. So to achieve 77 F1 score, it took 5 times lesser, like as they have mentioned it here, 5 times lesser training to achieve 77 F1, which BiDAF takes 15 hours, they just take 3 hours. The speed up game also allows us to train the model with more iterations to achieve better results. For instance, if they allow to train it for 18 hours, like from going from 3 hours to 18 hours, it achieves a F1 score of 82.7 on the dev set, which is much better and is on par with the best published results. On the squad, their augmented achieves 84.6 F1, and on the test set, which is significantly better than the published best 81.8. And in summary, the contribution is as follows. So they propose an efficient reading comprehension model that exclusively builds upon convolution and self-attention. To the best of their knowledge, they are the first one to do so. So the first ones to exclusively build upon convolution and self-attention for efficient reading comprehension model. And this combination maintains good accuracy while achieving up to the speed up that they do compared to RNN counterparts. So BiDAF model is the RNN counterpart. The speed up gain makes our model the most promising candidate for scaling up to larger datasets. Obviously, as we have seen now, 2020-21, we are getting massive models, language models, which are exploiting this convolution architecture. To the second contribution for the paper is to improve our results on squad. They propose a novel data augmentation technique, the back translation, by paraphrasing. They call it paraphrasing or back translation. It allows the model to achieve higher accuracy, which they say is the better than state of the art. The model. Now we'll look at the model. Problem formulation is context paragraph is there with n word, so you have a comprehension that you read, and there is a query sentence which is like the question. So Q, C would be the comprehension, Q would be the question, and S would be the answer. They call it S because it is a span, because it shows from which word to which word the answer lies for the particular question. So there's a start index and there's an end index, and all the words in between, those are the answer to the proposed question from the original paragraph. So now that we are clear with the problem formulation, C is the comprehension, Q is the question, and S is the span, which is the answer of the particular question from the comprehension itself. Now we'll go to the model. Yeah, I think this is good. So we have context, which is input, then we have questions, we input, and then we use pre-trained embeddings. We generate the embeddings for the words. Now these embeddings are passed through so the question and answer, the context and question, like the comprehension and the question, is passed through embeddings. The word embeddings are generated. Then we use something called as stacked embedding encoder models. Now we'll see there are two types of encoder models. First one is embedding encoder models, here and here, and second one is model encoder models. So here, here, and here. There are two types of different encoder models. Now the name varies from the input. So if it takes in word embeddings, then it's called embedding encoder, and if it is After these both embedding encoder blocks are merged inside the model, then it's called like a model encoder block. And the reason they are called stacked here are because you can see there is just one encoder block which is represented here, and there are multiple depending on the architecture that they have mentioned. So these could have multiple 7, 8, 9, 13, and even these could have different number of stacked encoder blocks like these. So hence the word stacked. Now once we generate the word embeddings, we pass it through a stacked embedding encoder block. Now what does the encoder block look like? As we see on the right, we have encoder block model, and what we do have is alright. So the first problem that we face when we move on convolutional neural networks for natural language processing is we lose the positional information about the words or the entire context that we are inputting. Hence, even in Vaswani et al, we have a positional encoding, or like all other convolutional neural network architectures, we have positional encoding embedded. So it could be as simple as just having the position number or the index 0, 1, 2, 3, 4, or you could have variations of sine cos functions and having multiple of functions, and then having like sampling the values for the particular word from the accumulated function. So in essence, it just identifies in which like what is the position of the particular word. Is it at the beginning of the sentence, middle, or end, or what is the position relative to each other? And that helps for the self-attention model that we'll have. After this, we have another block which is repeating. So not just the entire encoder block is repeating, there's another small block which also repeats, which is just layer norm. So you normalize the values for the tensor that we have over layers, so having a layer norm, and then a convolution layer. And this is with the skip connection, which allows the information to directly pass, or the gradients to directly flow back as well. And now this is repeated a couple of times. Then after this is repeated, so just layer norm convolution, layer norm convolution over the positional encoding. So it like abstracted at like a feature abstraction node. Then we pass it to another layer norm and self-attention. Now this is important. Self-attention is important. After the features have been extracted from the embeddings, then we have a self-attention block which will attend to the entire context that we have as input, and it will generate the key query context key query pairs and calculate the values and multiply and attend to the like self-attend to the input that we have. Now that is also, both of these blocks also have a residual block, are contained in residual block, and then we also again have a layer norm and a feed follower layer, which is a normal fully connected feed follower layer, and that is one encoder block. And the same block is used in the stacked embedding encoder models, embedding encoder blocks, as well as model encoder blocks. Now the number of times that they are repeated will be given in the paper. After we pass through the embedding encoder block, the context as well as the question, then we have context query attention. The context would be the comprehension, and the query obviously would be the question. So question will be querying over the context of the comprehension to figure out which part of the comprehension attends more to the question, hence giving us a clue of which part of the comprehension the answer will be in. And hence both of these are combined in context query attention. These are again followed by a stacked model encoder blocks, just as we saw here. These are multiple encoder blocks, and there are like 3 of these models, and the first output of this first block goes into both left and right, then left and right branches. The second output goes just to the left branch, and the third output goes to just to the right branch. Now the left branch gives us the start probability of the answer. So inside the comprehension, what is the starting position, like what is the word which denotes the starting position of the answer, and the right branch gives us the end probability. What, like in the entire sentence, let's say it's of 100 words, what is the probability that 73rd word is the end word? So you get a softmax distribution over the entire thing. And obviously, if you think about it, we also have constraints over this probability, that obviously the start probability, when we take the max of it, Re max of it, it should obviously be lesser than the end probability. So like the index, the start index should obviously be less than, strictly less than the end probability. But another addition to this, there is just one exception to this, is in squad 2.0 dataset. In squad dataset, we have questions. For every single question we have answers in the comprehension itself. So it has to be the index has to be lesser, start index has to be strictly lesser than the end probability. But in squad 2.0 they introduce twice as number of questions, and in the total dataset 50% of the questions don't have an answer. So the questions are either rated on the topic, but they don't have, the comprehension does not specify the answer to it, or it is the question is completely different. I don't think there are many questions which are completely unrelated to the comprehension, because the questions were curated by humans themselves, in a sense to the question to seem that it is related to the comprehension, but the answer is not there. So in that scenario, if that question appears and our model has to show that no, there is no answer in this comprehension, then in that scenario the way we solve the problem is just to denote zero index, and whenever start probability is highest for zero index and end probability is also highest for zero index, so in that case both are equal, start probability and end probability are equal and are equal to 0, only then we'll say that okay, that denotes that there is no answer in the comprehension. All right, so we'll see what we have. We have two inputs, that those are concatenated over the hidden regions, and even here we have to so the reason is we need more layers to comprehend and evaluate. Okay, right now we have this start probability information till this layer. Now we'll analyze the rest of the words and see till where. So we need more information and we need more compute to define what the end should be. So hence the later output goes to the right branch. That is at least my understanding. And we concat over the hidden layers. Then we have a linear layer to reduce the number of hidden states, and which is followed by a softmax, which is over the number of words in the comprehension. So that is the model architecture. Was it cut? Yeah, it wasn't cut. That's what they explain here. Input embedding layer, embedding encoder layer, context query attention layer, model encoder layer, and output layer. Data augmentation and back translation. Now this is like the first, we saw the first contribution now, the new architecture, and this is the second contribution. Since our model is so fast, we can train it with much more data. So they use two translation model, one translation model from English to French or any other language, and another translation from French to English to obtain paraphrases of the text. Now how this was done was they used we consider attention-based neural machine translation models, which have demonstrated excellent quality results. Specifically, they use the publicly available code base provided by this, which replicates the Google GNMT system, which is Google Neural Machine Translation. They train a 4-layer machine translation model, and the details like the what blue score they get and how many like what is the size of the dataset that they're trained on. Now what okay, we'll look at this diagram which explains the back translation very nicely. We have input sentence, we translate English to French. Now by way of translating, we have a concept called beam width, which gives different outputs which is like we have a beam search to get better results, and we have something called beam width, which in this scenario will tell us the number of translations that the model produces for an input sentence. So k being the beam width, will get k translations for this input sentence, and then all the over the k sentences, k French sentences in this scenario will again have a French to English translation over the beam width being k. So we'll have total k square paraphrases. So k into k, that is k square paraphrases, and hence input sentences will have paraphrase sentence which are like k square in number. So if I have k set to 5, then we'll have 25 translations. So we get 25 times the data. So that is the concept here. We'll see an example of what the original sentence was and how the answer. And they also mentioned, they mentioned it here that there were 25 paraphrases choices as they used k equal to 5. And essentially that's it. Like this is the essence of the paper is the model architecture and the back translation that they have. So they inform here how they handle this translation. Document paraphrasing, they paraphrase the entire comprehension D to D dash and answer extraction. So they have to extract, they don't translate the answer because it could miss, like the answer could completely change. So they abstract A dash from D dash. So the new generated D dash, they abstract A dash, or like they see which line is as close as A in that, so that they get an exact so hence so that they get start and end probabilities from D dash. And that's how they do it. They show a couple of experiments on different data sets and how they have like what results they have gotten. We'll just look at the performances of different models in squad dataset and appreciate the EMF1 that they have achieved. So you can see here, right about here, we'll have BiDAF, which came out in 2016. You can see it, it has 68 and 77.3 and 68 and 77.3 on leaderboard as well as published. Now there are some models which were not there on the leaderboard, hence or were not published. So hence the NA in these regions and in these regions. So QANet wasn't there on the leaderboard. Like the versions, these versions of the QANet, the final QANet was there on the leaderboard, obviously, and that got like the best. Obviously you can see they got the best results here, and the best published results were BiDAF plus self-attention plus Elmo. I'm sure that if we improve, so Elmo is like the language model representation. So in the word embeddings that we have generated in the beginning, if they have used that along with self-attention, so not BiDAF on its own, BiDAF with self-attention and Elmo, they lead it on the leaderboard. But as you can see, we also got like better results in 2000. We got 83.9 and 89.7 in 2018, which was like ranked number 1 on the leaderboard. So 84 and 90% was achieved by this paper, which is like a lot better than what they had achieved. But obviously I think the representation that they had used weren't Elmo, and they were a more basic word representation forms, and Elmo had just a new language model which was introduced. And obviously if we use better word representations, we would get better results. But yes, they hadn't published it, it was just on the leaderboard. So we can see BiDAF 68, 76, 8% better, 77.3 and 84, again 7% better. So you got better results, and like these results are the same. You got better results but with so much faster training and inference. So like that just gives us a idea of how they've given it here. The training for QANet RNN speed up It's, yeah, the speed up is tremendous. Here you get a 9.4 times speed up. Here you get a 13.3 times speed up. Here this is the speed comparison between their model and RNN based model on squad dataset. They have given the details of what these models were. So obviously, like, these are massive. The least speed up that you get is three times, and which is very good. And speed comparison between BiDAF. So like for 77, as you saw earlier, 5 times. Train speed was 4.3 times, inference speed was 7 times. And then they did more analysis and experiments. But yeah, like, this is it. This was the reason. Like, even they mentioned, like, this paper gives us the first implementation for the question answering system, like a big benchmark like squad, using convolutional neural networks and self-attention. And that is pretty exciting, and it pushed the limit. Like, it broke the broke into the leaderboard and inspired others to use this model and do further research. So that is very fascinating. And I'll put up the link for the R GitHub repository, the way that we have implemented it, and please go check it out. Thank you everyone for joining, as always, and I think with that we'll end today's stream. Thank you so much.